Excellent. Well, thank you all for coming today, and I want to say thank you to the organizers for having me. I've been to the Connecticut Number Theory Conference several times, and I've really enjoyed it. Today's talk, I'm going to talk a little bit about some heuristics for narrow class groups of abelian number fields. The work that I've done today is joint with Noam Elkies, Ela Varma, and John Voigt. And so to kind of briefly walk you through an overline for what I have planned for today, I want to start with a little bit of motivation. I want to kind of introduce the Cohen-Lenstra philosophy and kind of get people thinking along the ideas of what my research is and what I think about. I then want to talk a little bit about some of our conjectures and results, in particular for abelian number fields of odd degree. And then I've included so I'm going to talk a little bit about our conjectures and results, but I'm not going to really explain where the model comes from because that takes a little bit to set up. And so if we do have additional questions about where are our results and stuff coming from, I have some extra slides prepared for the model, but I won't give them in today's talk. So to just kind of start us off, if you take F to be a number field, you can, for any number field, you can associate a class group, which is just a finite abelian group for the purpose of this talk. And one of the things you can think about is that if you take a large collection of number fields, say like 1 million number fields, you can, for each of these number fields, you can look at their class group. And so you get this kind of large collection of finite abelian groups. And you can say, what on average do these finite abelian groups look like? So what does the class group of a general number field look like as a finite abelian group? How often might it be cyclic? How often might it be trivial? And to kind of refine this question, we can think, when you think about a finite abelian group, it's always constructed from the CeLO-P subgroups. So these are kind of the fundamental building blocks. And so I'm going to refine this in the following sense. I'm going to let P be an odd prime, and I'm going to let CLF P denote the CeLO-P subgroup of the class group. And so I'm going to narrow in and look at the CeLO-P subgroup of the class group. And what I'm going to do is I'm going to take another finite abelian P group, which I'll denote GP, and I can ask myself, how frequently do I expect the CeLO-P subgroup of the class group to be isomorphic to this fixed finite abelian P group, GP? And so this question was first kind of considered by Cohen-Lenstra in 1983 to 1984, and they looked at imaginary quadratic fields. And so what they found was that when you ordered imaginary quadratic fields by the absolute discriminant, the frequency for which the CeLO-P sub to this your favorite finite abelian P group is going to be inversely proportional to the number of automorphisms of that finite. So just to kind of work out a quick little example, we'll consider the abelian groups of order 9. So there's 2 abelian groups of order 9. First off, you can look at Z mod 9Z. And so this is a cyclic group generated by an element of order 9. And there's 6 other elements in that group that have order 9. So the number of automorphisms is 6. But you can also consider Z mod 3Z. So this group has, when you start thinking about it, this has slightly more automorphisms. In fact, you can identify this as being F3 cross F3, where F3 is the finite field of degree 3. And you'll have a lot more automorphisms in this case. In fact, you'll have an entire GL2 of F3 of automorphisms. So you'll have 48 total automorphisms for this group. And so if you look at the second group, you'll notice that there are 8 times more automorphisms. So there's a lot more symmetry for the second group. And so you'd expect these 3 groups to occur as the CeLO-3 subgroup of the class group in the relative proportions 8 to 1. So for each, for 8 times that you see the first group, you should see the second group 1 time. So the Cohen-Lenstra philosophy and kind of studying distributions of class groups is a very interesting question. And I'm going to take this in kind of a different direction for today. So I'm going to talk about some of our work studying what are called Ray class groups. So to set this up, we'll take M to be a modulus, which you can think about as just a formal product of an integral ideal and some collection or some set of the real infinite primes or just embeddings of your number field into the real numbers. And the class group is really the first in a collection of what are called Ray class groups, which are indexed by these moduli. And for any number field, you can associate this array class group of moduli M, and each of these is once again a finite abelian group. So you can play the same game once again. You can say, well, what on average do we expect these array class groups to look like? And this is the main bulk of what I do for a part of my research, is I focus on extending the Cohen-Lenstra heuristics to describe distributions of array class groups. So today, I'm going to focus specifically on two interlinked array class groups. So the first one is the narrow class group. So the narrow class group is formed by taking all principal ideals, and you want to quotient out by, you want to start with all fractional ideals, and you want to quotient out by principal ideals that have a totally positive generator, so some element that's positive in each of the embeddings. And the other array class group that we're going to look at is CL4 of F, which is the array class group of conductor 4. So I just wanted to make a quick remark. Generally speaking, when you think about array class two, you suppose you have kind of two array class groups, and they have different kind of disjoint moduli. You might expect that there's no kind of relation between those two array class groups, but there's actually a very interesting relation that, as far as I can tell, it only shows up for number fields. It doesn't show up for function fields between array class groups. And this is a very interesting relation between 2 and infinity. It's well documented in the literature. You can find, for instance, if you go into Neukirch's cohomology of number fields, there's an entire section just titled Relationship between 2 and infinity. And I want to just kind of briefly give a short description of what it is here. So if you take a number field with R1 real places and R2 complex places, and I'm going to need to talk about the M torsion subgroups of abelian groups. So this is just, I'm going to denote this with A sub M, brackets M, which is just the subgroup of elements whose mth power is trivial. And so to concisely describe the relationship between 2 and infinity, if you do look at the two torsion subgroup of the narrow class group and this array class group of conductor 4, you'll find that they're always linked by this following relation. So this says that this two torsion subgroup of the array class group of conductor 4 is always roughly equal to the two torsion subgroup of the narrow class group, up to this extra factor of z mod 2z to the R2. So there's this kind of mysterious relationship which links these two kind of separate kind of array class groups. And I'm not going to delve too far into this, but this shows up in a lot of the work that I do. And in particular, for me, this tells me that when I want to create a model for the narrow class group, I also have to really consider this array class group of conductor 4. These two things are kind of very interlinked, and they can't be treated separately. And also, I should say that a lot of the results that I have here for the narrow class groups also have analogous results for the array class group of conductor 4. So I'm now going to kind of briefly talk about some of my conjectures and results that we made for abelian number fields of odd degree. So to start off, Q be a abelian extension of odd degree, ZF cross be the units in the ring of integers, and I'll let GF denote the Galois group. So when we look at the Galois group, it acts on lots of different. In particular, it's going to act on the set of fractional ideals, and this induces an action onto these array class groups. And in particular, it's going to transform the two torsion subgroups into what are called F2G modules. So this is, here I'm using F2 brackets G to just denote the group ring there. And I just want to make a kind of a quick note here that since I'm requiring our Galois group to be odd, the reason that I'm doing this is because I want every F2G module to be semi-simple. I want it to break down into a direct sum of kind of irreducible modules. I don't want to kind of play around with the irreducible versus indecomposable. So before I kind of present some of the results that are known here, I need to just kind of briefly talk about duality for F2G modules, and in more general for kind of group rings. So you'll note here that I've dropped the little f from the groups. The reason is that when I talk about duality, these are going to be kind of purely algebraic results. They're not going to have to do anything with number fields. So I'm just going to take G now to be some finite abelian group of odd order. And I think the best way to describe duality is if you do have an element of your group. So you pick an element in a group, there's a map G goes to G inverse, and this is going to induce a map on the group ring from F2G to F2G. And so what we can do is you can say, if I pick some irreducible module V, we know that it occurs somewhere in the decomposition of the group ring as a F2G module. And I can define the dual module as just what happens under this map. So I take my irreducible module V, I identify it as being inside F2G, and I just look at what happens when I act on it with this map. And so once we've defined it this way, you can, this is defined for irreducible modules, but you can, of course, kind of lift it to any F2G module M because they're all semi-simple. And we also want to talk a little bit about what it means for a module to be self-dual, which is if it's, as an F2G module, is it isomorphic to itself? These are, you can think about this map on the group ring as being an involution, and these are the fixed points under the involution. And so I just want to take a brief moment to kind of revisit this relation between 2 and infinity, between the two-adic places and the real places. Generally speaking, we had that relation that I stated at the very beginning, and that holds for any number fields. But if you go further and you say, let's look at odd Galois number fields, what happens is because your field is odd, then there's at least one real place. And because it's Galois, that means all the places are real. So you have a totally real field. And that immediately tells us that these, the two torsion subgroups, based on my initial relation that I showed everyone, that those are same size. So the two torsion subgroups are same size, but further, they're actually going to be dual to each other as F. So this is what's kind of classically known as a reflection theorem or Spiegel-Ansatz. And I'm attributing this theorem to Gross. It can be proven from his reflection theorems, although he never states it explicitly. And eventually get there from his kind of very general, what are called ST reflection theorems. So I think this is just a very cool result and an interesting kind of fact when you're studying these groups. So lastly, before I state some of our results, I just want to briefly touch on when is every F2G module self-dual? So F2G modules, so in the case that they're semi-simple, they always break apart into irreducible modules. So these are like the fundamental kind of building blocks. And there's only a finite number of irreducible modules. So if each of those irreducible modules is self-dual, then every F2G module is self-dual. And so we want to ask is it possible that every F2G module ends up being self-dual? And there's a very simple criterion to detect when there actually are non-self-dual F2G modules. So what you can do is you can look at the exponent of the group, which I'll denote M, and if -1 is a power of 2 in Z mod MZ cross, then every F2G module is going to be self-dual. Conversely, if -1 is not a power of 2 in Z mod MC cross, then there are going to be non-self-dual modules. So just to list some examples, if we look at Z mod 3Z, you'll see that, I guess for the examples that I'm going to show here, each of the groups are cyclic, and so the exponent is the same thing as the order of the group. And you'll note for this one that 2 is automatically equal to -1 in Z mod 3Z, so every module is going to be self-dual. For 5, you'll see that 2 squared is equal to -1, so every module is self-dual once again. But if you move up to degree 7 extensions, so G equals Z mod 7Z, you'll see that 2 squared is 4, but 2 to the third is 1 again. And so -1 is not going to be a power of 2. And there are actually 2 irreducible non-self-dual modules in this case. So now I want to kind of briefly describe some results that we get at. And to do this, I want to contextualize it a little bit by describing the relationship between the narrow class group and the class group. So generally speaking, whenever you have a ray class group, it's always slightly larger than the original class group. And for the narrow class group, it's only going to differ from the class group in its 2-CELO subgroup. So what we look at, and in particular what this talk is going to focus on, is just the 2 torsion subgroups. So we're not going to try to cover the entire 2-CELO subgroup. We're just going to focus on the 2 torsion subgroups of these 2 groups. So the first theorem that I want to state was due to Taylor and Oriot, and they looked at abelian number fields with odd exponent m. And so the exponent is coming here. the fact that I stated earlier. So if you have every F2G module being self-dual, equivalently -1 is some power of 2 mod m, then the two-torsion subgroup with the narrow class group and the class group is the same. So there's no difference between their two-torsion subgroups. And this covers the first kind of the smallest cases that we can consider if we want to do cyclic cubic fields and cyclic quintic fields. So for these two cases, the narrow class group and the class group their two torsion subgroups are the same. So the first interesting case happens for cyclic number fields of degree 7. In this case, the subgroup of the narrow class group is highly dependent on the two torsion subgroup of the class group. So to briefly kind of get into this, if the two torsion subgroup of the class group is not self-dual, so there's some kind of asymmetry to the two torsion in the class group, then the narrow class group is going to be slightly larger. It's going to have this extra factor of z mod 2z to the cubed, and it's actually going to become self-dual, which is pretty cool. So that's actually an explicit theorem. We then studied what happens when the class group was self-dual. And in this case, we had to use our model and make heuristics and conjectures. And so in this case, we found that when the two torsion subgroup of the class group was self-dual, we expect the two torsion subgroup with a narrow class group to be isomorphic to it with probability 7/9. And otherwise, with 2/9, it'll have an extra factor of z mod 2z cubed. So to kind of summarize, one of the main interesting points that we found here for when we have non-self-dual modules is that class groups and ray class groups, or sorry, the class group and the narrow class group want to be self-dual. To kind of illustrate this is if the two torsion in the class group is not self-dual, then the two torsion in the narrow class group suddenly becomes self-dual. And similarly, when the two torsion in the class group is already self-dual, then it's very likely that the narrow class group is also just going to be self-dual. So we found this really interesting that these ray class groups wanted to be kind of self-dual two torsion subgroups. So I'm going to briefly conclude with some results in heuristics for unit signature ranks, which is another thing that our model yields. So to briefly describe this, the unit signature rank is the dimension of the image of a group homomorphism, which takes a unit and you embed it into each of the real places, and you just record at each real place whether that unit is positive or negative. So you get this tuple of signs, kind of plus or minus 1. Okay, yeah. Oh, sorry. I think there's a question. But I guess I'll check back in and answer that at the end. At least for the opening of the question, I believe, so we don't actually.
Can you hear me?
Yes.
Question as how often do you expect the two-part of the self-dual?
We don't actually know. So Mala makes heuristics and we trust his heuristics for cyclic cubic fields and cyclic quintic fields, but we weren't sure what his heuristics would yield for degree 7 extensions. And computationally speaking, I wasn't able to eke out anything more than like the first 8,000 fields for magma. Using magma, I wasn't able to eke out kind of more than the first like 8,000 fields for degree 7 extensions. So I don't have a good idea just yet. I'm hoping that this can be answered at some point in time, but I don't know how frequently the class group should be self-dual, particularly in that case, but more generally. So, okay, sorry. So getting back into unit signature ranks. So you can take these units, you can record their signs, just plus or minus 1 at each place. And one of the things you can think about is what is the dimension of the image in the space that's formed by taking all the infinite places and just kind of looking at plus minus, plus minus, plus minus. And so the unit signature rank is going to be bounded between 1 and R1. So the lower bound 1 occurs because every number field has minus 1, and that embeds as negative, 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 negative. The upper bound occurs when you have units of all possible signs. This means that there is no difference between principal ideals and principal ideals with a totally positive generator, because you can change any, if you have any element, you can change its signs by a unit to make it totally positive. And so this occurs only when the class group and the narrow class group are the same. So we then looked at cyclic cubic number fields. So a cyclic cubic number field has unit signature rank either 1 or 3. The reason that unit signature rank 2 doesn't occur is that if you do have a unit of mixed signs, so say like positive, negative, negative, the Galois group is going to act on that unit and it just kind of permutes those signs. And so you'll actually end up with all possible signs. If you have any unit of mixed signs, you'll end up with units of all possible signs. This also has to do with kind of the Galois module structure. And you can ask, well, how frequently do each of these cases occur? And so our model predicts that as you vary over cyclic cubic number fields, the probability that you have unit signature rank 1 is approximately 3%. So we believe that 3% of cyclic cubic number fields have units that are either totally positive or totally negative. This means that the other approximately 97% class group and the narrow class group are equal. They're isomorphic, which is a really interesting kind of fact. And second, so we looked at if we could prove anything about what percentage actually have unit signature rank 1. We weren't able to establish any positive proportion of number of cyclic cubic fields, but we were able to show that there's infinitely many cyclic cubic number fields which have unit signature rank 1. And this is a very interesting result. It's very different from the work that I standardly do, and it involved some parameterizing curves on a log K3 surface with GNOME. And so I just want to conclude with some computational support for heuristics. So whenever you make heuristics, you should support them in some sense. And we decided to look at sampling cyclic cubic number fields with large conductor. So we designed an algorithm that can go out and grab a random sample of cyclic cubic number fields with conductor bounded in a box of size X. And here you can see that we set the size of the box. Initially it's 10 to the 5th. We raised it to 10 to the 6th and 10 to the 7th. So this is the bound on the conductor. And we found when we looked at these samples of 10,000 fields, we found that approximately 2.3% had unit signature rank 1, 2.4% and 2.6%. So we believe this is slowly converging to our predicted value as you kind of raise the bound on this conductor here. So that's all that I have for today.
Thank you.